Well, it's 11 here, but maybe a bit early to talk about dust there. We'll go for it anyways. Okay, so anytime we have a powered landing on the moon, we have this exhaust plume from the lander that hits the surface and kicks up dust, fine regolith, maybe some larger regolith, and how much dust and regolith we kick up and how far and fast it goes actually depends on many things related to the lander and the surface. So on the lander size, we care about things like the size and shape of the nozzle, the engine configuration. So if we have one thruster or four, maybe the composition of the exhaust, the thrust, and of course how that lander is either descending or ascending. So its altitude and its velocity. Then on the surface size, we have very important things like the grain properties. So the size, shape, density, maybe coefficient of restitution of the grains. We have some gas grain thermal effects. How far and how much dust gets picked up is actually affected by the temperature at the surface. And of course, things like the surface roughness, inclination, and gravity is going to have a large effect. Now, in our study, we are interested specifically in the size of the lander, like its thrust, how it's ascending or descending to the surface, the different properties of the grains, and then we're also interested in gravitational acceleration because we're looking at this initially on the moon, but there will be some plume surface interactions, different thruster experiments and other bodies like Phobos in the future. So gravity is a parameter of interest as well. Okay, so to get an idea of how fast and far this dust is going to go for different configurations, we have a two-step approach. We start with the direct simulation Monte Carlo method, DSMC, and we create lander plumes. So I'll talk about this step first. What I'm going to show are some videos here. The first one I'm going to play is the number density of gas molecules. And on the left side panel is a large lander like the Apollo lander, and right size is something like the Chunga lander. So as the lander goes down, we see that we have the number density of these molecules increasing as we get near the surface, and then they stop. Right-hand side is same video, but this time we're looking at the velocity of the gas. So here, if you look at the evolution of those red, dark red regions, these are really where you have, and I'll play that one again, the highest velocity. And this is where if you have dust that gets kicked up in there, it's going to be accelerated and thrown the furthest from a landing site. So what we do is we use DSMC to create these plume fields, and then we propagate them out far from the landing site. So again, on the left-hand side, we have a plume for an Apollo-like lander. Right is a more mid-sized Chunga-sized lander. And this is the plume field as it's expanding on the moon, far from the landing site. You see here up to 150 meters. And so after, as we move further and further away, we have this more dilute gas. And what that means is that the gas is going to have less of an impact on the dust, and the dust is going to have more of a ballistic trajectory. And this is important because it's kind of feeds into the next step of how do we predict where this dust is going to go. So what we do is we use this Lagrangian method in MATLAB where we take our plume field that was generated through DSMC and we drop in a dust particle at different places in this field. We can change the gravity, we could change the plume field, we could change the size of the particle. And then we use a drag force that's generated by this plume field, and it's accelerating that dust through the plume field. And then at a certain point, whenever the dust is, or the gas is dilute enough, then we just consider we have this purely ballistic motion of the dust, and we see how far it goes and where it lands.
Hey, Cecily, I'm
So
so
the
sorry to
forces
interrupt.
that are,
Sorry to interrupt, Cecily.
yep,
There's a little pop-up on the bottom of your screen share. Do you mind clicking the hide button? It's covering some of your graphics there.
oh, yep, sorry.
Thank you so much.
Thank
Sorry
you.
about that.
Yep. Okay, yeah. So this is the kind of the same image before with these different gas molecules, number density of the gas in the plume. And so again, we drop in our dust. We have a drag force that's created that we calculate from this flow field, and then we use some ballistic equations to see where that dust goes. So here in black, we see what a streamline of the gas looks like. And the star is just an example. If I drop in a 2 micron dust particle, the red dotted line is where that dust actually travels within the flow. And then whenever it crosses that threshold of 30 meters from the nozzle center line, we see where it goes. Now, we do the same exact thing, the same calculation for every single point within this red box here. Because as we're landing and eroding the surface, this is really where the dust is going to get kicked up into the flow. And when we're running our calculations, we could do different initial conditions for the dust, like different initial velocities. But right now we're just saying an initial velocity of 0, anywhere within this region, where does that dust go? So on the left-hand side here, we have the Chonga size lander, and on the right-hand side, we have the Apollo lander. And with showing 3 different hover altitudes of the landers. So the top is 15 meters, middle is 10, bottom is 5. These are for 2 micron dust particles. And the colors here show the horizontal travel distance of that dust at these different lander altitudes. So as we get further closer to the surface, we see that the dust is traveling further. We see that close to the nozzle center line, we have this region where the dust really isn't traveling too far, where it's getting picked up and traveling the furthest is in that high region where we saw that high velocity flow to begin with. And of course, we see a big difference between the size of the lander. So about an order of magnitude difference in the distance with the lander size. This time I'm showing on the left, same panel, 2 micron dust particles. And on the right here, if we had 20 micron. So much larger particle sizes. So still small enough that it's considered dust, but about 10 or an order of magnitude bigger here. And we see that, of course, I think as we would expect, that dust is traveling much lower. And I just want to note, the scale down here is in meters. So we could have stuff that's traveling hundreds of kilometers or just a few tens of meters. Now, what if we were to look at a 5-meter hover of these landers and we let the dust pick up all along the surface? Where would that dust go? So this is a steady state simulation here. We're looking at the number of dust particles deposited per meter squared at the distance from the nozzle center line here. The red is the smaller Chonga lander and the blue is the Apollo lander. And you can see closest to the nozzle center line is where we have most of the particles deposited, but as we move further out, we could have particles deposited up to 100 or 300 kilometers from the site. So here, picking Addie's home location there around Orlando, we show how far that dust is actually traveling if we were to land in Orlando. And in the Apollo case, we are littering particles all over the state and into the ocean. So it's quite impressive and quite further than we would expect.
We have about 1 minute.
So okay, great. This is just wrapping up now. So kind of we have these interactions that are really complex, really dependent on the properties of the lander, the properties of the surface, and I haven't actually presented anything to down the gravity, but you can imagine you take gravity away and this ballistics change completely. You have particles that are really going to possibly leave your body, depending on the one that you're landing. I didn't give the specifics on the travel speeds, but these small dust particles are actually exceeding 500 meters per second, which is quite literally faster than a speeding bullet. And they could travel over hundreds of kilometers from a landing site. So we're still working on this. We're continuing this. We're doing a bigger range of particle sizes, looking at things like how coefficient of restitution affects our results, and of course, gravity. Just last thing, I'd like to say thank you to the NASA postdoctoral program and Survey for funding my postdoc. So this was made possible by them. Thank you.